As you can see, acids are corrosive and seem to be harmful. However, there are many acids present in your food. Citric acid in lemon, acetic acid in vinegar, and so on. But you don't fall ill from eating these acids. So what's different about the acids present in acid rain? Are bases also corrosive, as are acids? To answer these questions, you need to understand the properties of acids and bases. Let us first look at the properties of acids. All acids are corrosive in nature. Mineral acids, such as concentrated sulfuric and nitric acid, can cause damage to organic materials such as skin, cloth, paper, and wood. Acids can even wear away stone. In addition, they can corrode metals such as iron, aluminium, and so on. However, acids can be strong or weak. Mineral acids are strong acids, and strong acids corrode material quickly. Acid rain is so called because it contains mineral acids and is therefore harmful to all sorts of organic and inorganic material. Weak acids are less corrosive than mineral acids and take a long time to damage material. Acids found in food products such as acetic acid and citric acid are weak acids. That's why you can eat substances such as grapes and curd and have lemonade and fizzy drinks without experiencing harmful effects. You have just learned that weak acids take a long time to damage materials. Do you think it is safe for you to touch or taste dilute acids? Not really. Dilute and concentrated acids are different from strong and weak acids. A dilute acid is prepared by adding concentrated acid slowly to water. Thus, a dilute acid is simply a solution containing a low concentration of the acid. So it is always unsafe to touch or taste mineral acid, whether it is concentrated or dilute. You may have noticed that acids display their properties only in solutions with water. Acid rain is also a solution of acid in water. This also means that acids dissolve in water. Let's look at the composition of acids. Hydrogen is one of the elements of all acids. Acids have combined hydrogen. A large number of metals, such as zinc and iron, react with acids to evolve hydrogen gas. Here is a summary of the properties of acids. Strength of acid and its concentration have vital roles in various fields. What do we mean by the strength of an acid or base? Does it represent the concentration of acid or base present in a given amount of solution? Or does it represent the nature of the acid or base? The term concentrated indicates that more moles of acid than normal are dissolved in a given volume of solution. The term dilute indicates there are fewer moles of acid in a given volume of solution. The concentration of the solution depends on the level of acid or base in solution. The term strong indicates complete ionization. The term weak indicates incomplete dissociation. The strength of the solution depends on the nature of the acid or basic solution. When acid dissolves in water, it gives H+ ions. Example, hydrochloric acid gives H+ ions and Cl- ions. When base dissolves in water, it gives OH- ions. Example, sodium hydroxide solution gives OH- ions and Na+ ions. The strength of an acid or a base depends on its degree of ionization in water. Strong acids and bases completely ionize in water. Example, sulfuric acid is a strong acid since it ionizes completely. Sodium hydroxide is a strong base since it ionizes completely. Weak acids and bases partly ionize in water. Examples, acetic acid and ammonium hydroxide. Can survive in a narrow pH range between 7.0 and 7.8. When the pH of rainwater is less than 5.6, it is called acid rain. This low pH kills most aquatic life. Some plants grow better in alkaline soil and some grow best in neutral soil. Rotten roots produce acids in soil. If they are not removed, the soil becomes acidic, unfit for the cultivation of most plants. Sometimes acidity is neutralized by adding alkaline salts to the soil. We digest our food with hydrochloric acid produced by the stomach. If the same acid is produced in excess, it affects the gastric layer and causes ulcers. The acidic pH is reduced by taking an antacid, which contains bases such as aluminium hydroxide or magnesium hydroxide. Our teeth are coated with an enamel of calcium phosphate. Our saliva maintains the pH of our mouth in the alkaline range. Food particles sticking to the teeth are usually attacked by bacteria, so that the pH level in the mouth falls. The acid produced by bacterial action attacks the enamel and results in tooth cavities. The alkalinity of toothpaste neutralizes the acidity produced by bacterial decay. The acidic pH range supports bacterial action in milk. So in dairies, milk is treated not to allow the pH to fall below 6.6. Certain biochemical reactions occur at some fixed pH values in industries such as breweries and food processing units. Clinical laboratories regularly test the pH values of blood, urine, etc. to diagnose certain diseases. pH values are very important in cosmetic products such as shampoos, face creams, soaps, deodorants. Insects use pH as a defense mechanism through what is actually chemical warfare. The sting of a wasp contains a base that causes irritation and pain to the person's tongue. Can we neutralize the basic pH by applying an acidic solution? Yes, we can apply lemon because it contains citric acid. When ants bite us, formic acid enters the skin and causes itching. We can apply calamine, a solution of zinc carbonate, to the affected region to reduce the itching. The plant nettle has very fine hairs that contain methanoic acid. When we accidentally touch the leaf, it injects this acid into the skin and causes irritation. This irritation can be reduced by rubbing with baking soda paste or soap or a dock leaf. Common salt or sodium chloride is a physiological necessity for human life, equal in importance to water. Primitive man, the hunter and gatherer, obtained his salt and protein needs from the blood and meat of his prey. For the civilized man, however, the known mineral sources of salt were limited to exposed outcrops, dried salt cakes in lagoon areas, and on the shores of seas and salt lakes. This is probably why some of the first great civilizations first developed near deserts and close to known salt sources, for example, the Harappan civilization, Mesopotamia, and Pharaonic Egypt. The use of salt as the best known food preservative further helped in the growth of civilizations. Man could now travel and explore great distances without fear of meat, fish, and vegetables going rancid. In ancient times, trade in salt was very important, and salt was valuable enough to be used as currency in some areas. Apart from its historical and physiological importance, sodium chloride is also a raw material in the production of many useful chemicals. Some of these are used in our day-to-day lives, such as sodium hydroxide, baking soda, washing soda, bleaching powder, and many more. Let us see how one substance is used for making all these different substances. When sodium chloride is dissolved in water, we get an aqueous solution of sodium chloride. This solution contains sodium ions, chloride ions, and also hydrogen and hydroxide ions from the dissociation of water molecules. When electricity is passed through this solution, movement of ions towards the oppositely charged electrodes takes place. Hydrogen gas is produced at the negatively charged electrode, called the cathode. Chlorine gas is produced at the positively charged electrode, called the anode. Sodium hydroxide is also produced near the cathode. This process is called the chlor-alkali process because of the products formed. Chlor stands for chlorine and alkali for sodium hydroxide.